Where we left off is our next section here is entitled Authentication Fundamentals. And so we're going to talk about some things related to authentication and authorization. Now, I think as I kind of said during the introduction, when we talk about authentication in a web app, it is a very, very vast topic, okay? When we do sort of the full length security class that's, like 4 days long, we'll usually spend almost a day and a half just on authentication and authorization issues and topics and things. So for us, for this training for 1 day, our goal is to just kind of take a survey of what are some of the different authentication options that are out there, why you might pick one versus the other, how you sort of match up which authentication mechanism you choose compared to what your requirements are, right? Sometimes we talk about authentication. What I like to do is I say, well, these are the different mechanisms I have, the different ways to approach authentication. These are sort of my application requirements. And what I like to do is sort of say, well, what's the simplest authentication system that I can use that meets my requirements? Because sometimes what I see people do is they'll pick some super fancy, crazy authentication system with lots of bells and whistles and everything on it. But in the end of the day, they end up with a less secure system than if they would have picked something much simpler to implement. Because, it's kind of like, again, security for your house, right? I can put a lock on my front door, or I can buy some sort of, crazy motion detection system with lasers and all this other crazy stuff. But if I don't understand how that system works and how to configure it properly, it may not be anywhere near as effective as just having the lock. So sometimes complexity can come back and get you, right? So a more secure system that's not used properly is typically less secure than a less secure system that is used properly. So I try to pick the simplest one I can that meets my requirements, right? Bottom line. The other thing we want to do in this section is we want to just kind of work through some terminology. Because when we talk about authentication and authorization, one of the major challenges is making sure that everybody's kind of speaking the same language and understanding some of the terms and things. And so when you're having like a meeting or a discussion where you sort of decide on what kind of authentication system to use, making sure everybody's kind of using the same words and speaking the same language is a big win, right? And so you can have an intelligent discussion about why you might choose one versus the other. So this first section here, authentication fundamentals, is kind of about the terminology part of things, and then we'll go through kind of a list of some of the different ways we can do authentication in a web app. So first of all here, when we talk about authentication, this is the process of figuring out who the user is, okay? Discovering the identity of an entity through an identifier. So in other words, the client is submitting some sort of identifier, which is kind of a claim of who they claim to be, right? And then verifying the identity, so we can now trust or believe the information contained in that identifier by validating the credentials provided by the entity. So we have the identity and credentials. This is who I'm claiming to be, and you can believe that because here's some sort of credential that you can validate or verify, right? So the simplest form of this, of course, is username, password, right? The credential tends to be the sensitive bit, which is something we don't want to be, compromised or what have you, where the identifier is something that usually we don't care if people know, right, as much, what my username is or email or whatever it happens to be. So all of the different types of ways we can do authentication still just center around the same concept, okay? What we're using as the identifier may change, and what we're using as the credential may change, but it's still the same idea, okay? All right. So the credential, the thing that we use to validate the identity, to prove that they really are who they're claiming to be. Well, when we talk about credentials, credentials can fall into one of three different sort of categories, okay? We call these sort of our credential types or our kind of the factor. So a credential can be a knowledge factor, right? That's something that the user knows, or the way I like to think about it is a knowledge factor would be something you can tell somebody over the phone, right? Like a password or a PIN, right? The next different kind of credential we could have is something which is an ownership factor, okay? An ownership factor is not something that you know or that you could tell somebody over the phone, but something you possess, right? That you could maybe still give it to somebody else, but it's a little bit more difficult, right? So something like a certificate or a hardware device, like a little USB key or something that you have to insert into your system in order to access the remote device, yeah? Or we could have an inherence factor. So an inherence factor isn't something you know or something you possess, but something about like who you are, okay? So like a fingerprint or facial recognition or a retina scan or something, right? Now that's one you really can't give to anybody else. Now, of course, I'm sure you've seen, some scene in a movie somewhere where somebody has stolen some guy's eyeball and used it to get into the, retina scan thing, whatever, but movies. And you've probably also seen things like videos and stuff online where people have figured out ways to get around different fingerprint scanners or Face ID on an Apple device or whatever. There's a really great Mythbusters episode of actually them testing different fingerprint-based locks. But anyway, even with that though, you can imagine that these are we're kind of moving up the ladder here, right, in security. And so kind of associated with this though is this idea of two-factor authentication. Now, this is one thing that sometimes people misunderstand, which is when we're talking about two-factor authentication, what we're really saying is in order to be authenticated by the system, you have to provide two credentials. One credential is from one category and one credential is from a different category, okay? If to access your system, I have to provide a knowledge factor like a password and a second knowledge factor like a PIN, that is not two-factor authentication, okay? Okay, because it's two knowledge factors, it's one knowledge factor that's just split into two pieces, okay? So to be two-factor authentication, it has to be something from two different categories, okay? So like, for example, if I'm using, if I have an account with Apple and I'm trying to update my Apple account, what may happen is I have to supply my password, knowledge factor, and then it says, oh, well, wait, before we let you in, we're gonna have to send you some sort of code to your phone, right? Either your text message or something. And that's an ownership factor because in order for you to receive that text message, you have to have possession of your phone, right? And so they consider that an ownership factor, okay? Or a lot like with my account on Amazon Web Services, I provide my password and then it comes up and asks me for my Google Authenticator code. So I open up my phone, open up the app, and then I look at what the current code is for that and then whoop, type that in. So this is also considered an ownership factor because I have to have possession of this phone with this app on it, okay? I made the mistake one time of selling my phone and getting a new one, and then I forgot I had two-factor on a bunch of sites, and I was like, oh, yeah. And it was kind of a pain to have to jump through all the hoops to get that resolved. But yeah, okay. I mentioned the defense message system the other day that I worked on in my time at the Pentagon, and for that system, the way it worked is if General A wanted to send a message over there to General B, General A was issued a Forteza card, which is basically a PCM CIA card that had the encryption hardware on it. And so when he wanted to send a message, he would take his Forteza card, he would insert it into the system, and then the card would actually prompt him and ask for a PIN, type in the PIN, and then he could write his message and send the message. General B, to receive the message, put in his Forteza card, supply the PIN. So two-factor again, because you had to have possession of the Forteza card and know the PIN. Later, we switched from using a PIN to biometrics. So it went from knowledge ownership to ownership inheritance, okay? But yeah, two-factor. So if you want to implement two-factor authentication in your own applications, just a few things I'll say about that. One, it's kind of good because it's becoming much, much more prevalent now, more popular. So it used to be if you forced your users to use two-factor authentication, your users were sort of unhappy about that because it was an inconvenience. And they're like, what is this? Why does LA County require me to have to do this other thing and I've got to get the text message or the what? But nowadays, if you were to actually implement it and do it, most of your users would probably say, okay, yeah, just like what Apple does, or just like what Google does, or Facebook, or whatever. They've probably been through it before, they're accustomed to it, they're getting more used to it, so it's not as big of a deal. So that's good, okay? The other thing I'll say is, you might not require two-factor authentication for everything. So for example, in your web application, you may require your user just to provide a password to sort of get into their profile or whatever it is. But then if they go to do something that's considered more sensitive or more destructive, like deleting their account or changing their email or something, then at that point it may trigger something that requires that second factor, right? And so it's like, well, in order to do that, we need to send you this code, email, whatever it happens to be. So, but it's a good tool to have at your disposal and sort of use it when it's appropriate in your applications. There are also some really great third-party libraries, as well as now in ASP.NET Core with ASP.NET Identity, there are some built-in capabilities in the framework for implementing two-factor authentication. So you can very easily, within like less than half a day, implement two-factor authentication using the Google Authenticator app, just by plugging a few things into your app. So that can be beneficial as well, right? But again, you don't want to go too far off the edge into the inconvenient part, because then your users just sort of get frustrated and unhappy, right? So you have to find that balance again. All right, so multi-factor authentication is great when possible. It's great to use. But some other best practices here with authentication. One, do not deploy an application with default credentials. Okay, what does that mean? Well, you know how we've heard in the past years that when you go and buy a consumer device like a router or a baby camera or whatever, it comes with some default username and password, and most people just don't change them. And now people know what those are, and so next thing you know, baby cams are being used to launch denial of service or mine Bitcoin or whatever. So if you're, say, building an application that you then provide to other people for them to use, you typically don't want to bake in some sort of default username and password or something, because the users won't change it or something like that. So this may not be a concern for you because you're not in this kind of role. But if I'm building like a CMS system or something that I want somebody else to use, the first time they go to set up the system, I'm going to require them to provide some credentials for like the default account or the admin account. I'm not going to like bake one in, okay? Because it's just asking for trouble. Or another way to look at that is whenever you are using an application provided by somebody else or some sort of, you know, third-party content management system or whatever, you should be aware of if there is some sort of default account and make sure you change it. Okay, you look at it from the other side too. Implement weak password checks. So there are lists of common passwords that are out there that are available, and so it's a good idea to kind of. So let's talk about password complexity and things a little bit. So I actually had a question that was asked during the morning session, which was kind of funny, which was, so somebody online asked the question when I was talking about password complexity, and they said, oh, like the correct horse battery staple. I was like, yeah, exactly. So when we talk about password complexity, what we really don't want to do anymore is do this whole thing of when users create their account, and then you tell them, oh, it has to be at least 8 characters long, contain at least one symbol and one lowercase letter and one uppercase letter and one, okay? Because that just frustrates users, it drives them crazy, and it forces them to create passwords that are very, very difficult to remember, but actually aren't really as secure as you think they are, right? And so the example here given by this little comic strip here, which is what the person in the morning session referred to, is that up top there, we have our user choose a password like TR0UB4DU0R3. Looks very complicated and very, you know, ooh, random. But the truth of the matter is, if we look over here, that based on how much complexity there is in that, at 1,000 guesses per second, it would take 3 days to find that via brute force methods, right? To go through all the possibilities. On the other hand, if our user was to pick a password that's just made up of 4 random words, like correct horse battery staple, okay, it's much, much easier to remember. And actually with that, if we look at the complexity there, at 1,000 guesses per second, it would take 550 years to brute force all the possibilities there, okay? And so it's probably better to encourage your users to create passwords like this than it is to create these symbols, numbers, uppercase, lowercase, and all that business, right? So you'll see a lot of sites now moving away from those really wacky password requirements. Now, having said that, you should still have some password requirements. Like you can't have people create 2-character passwords, right? So there should be some length requirement, okay? But the other thing you may want to do is instead of having them, you know, use all these funky symbols, you can get a list of sort of dozens, hundreds, or thousands of the most common passwords, because there are organizations that publish these anonymous lists of what the most common passwords are. So here you can see these are the top 10 most common passwords. So the first one, yeah, QWETRTY, you just go across top of the keyboard, right? Password 11101, 1234678, ABC 123, 123. And the truth of the matter is, even if you force them to use all sorts of funky symbols, they're going to find the shortest path to get past that, right? So they'll end up doing password, but uppercase P, use an @ sign instead of an A, and a 0 instead of an O, and you still end up with password, which is still going to end up being a very common guessable password, even if it's got all those requirements. So what you can do then is in your applications, if you have sort of a list of the common passwords, when somebody goes to create a new account, you can compare what password they're choosing to that list of commonly used passwords, and then give a message that says, hey, this is a really common password, please don't use this, okay? The other thing, what about like password rotation? So forcing users to change their password. Well, this is, again, that's gonna be another one of those balance, right, between convenience and security. So it'd be nice to force your users to change their password like every week, but users aren't gonna like that. So you have to decide on what a good balance is there. And plus, I also like to give the user some warning. Like when they log in, give them a message that says, hey, you're gonna have to change your password at some point in the next 30 days. And then you have 10 days and you have 5 days. And instead of just like all of a sudden out of nowhere telling them, hey, change your password. Because then they're like, oh, really? The other thing is I do like to typically maybe keep the hashes of their last few passwords so that when they do change their password, they can't use one that they've used the last like 2 or 3 times. But you decide what to do there, right? How far to go. Use the same message for all account-related failures. Basically, what I'm saying here is if the user types in an improper username, tell them, sorry, invalid login. If their username is correct, but their password is wrong, tell them invalid login, right? Don't tell them invalid password if their username is right, but their password is wrong. Because what that becomes is a very useful way for an attacker to discover valid usernames. Because I just start submitting all sorts of different usernames. Invalid username, invalid username, invalid username, invalid password. That's a valid username, right? And we don't want to give up that information. We are taking away a little bit of convenience from the user because they don't know which thing they messed up, but it's worth it in that case, I think, right? Limit or increasingly delay and record failed login attempts. Okay, so this is the one where, if you supply an incorrect password, say 5 times in a row, we lock out your account, okay? Now, this is one that's potentially pretty easy to implement because if you got your user table with your, usernames and passwords, passwords are not clear text, we'll store the hashes, we'll talk about that later, but I can just add some additional columns there. One is, number of failed login attempts, and one is locked out, true or false. So every time they log in incorrectly, we increment that count. Once it hits like 5, we flip locked out to true. They can't log in until somebody goes in and resets that back to false, right? Once they do successfully log in at any point, we make sure we reset that failed count to 0, okay? Now, here's the thing I don't like about that approach, just stopping there. If somebody's trying to sort of brute force their way into the system and they're just trying all sorts of passwords, they could end up sort of locking out legitimate users. And I don't really like that to happen. So what I'll do instead is sort of this delay feature. So what I'll do is, okay, somebody tries to log in with the username Bill, but the password's wrong. Okay, so wrong password, wrong password, wrong password, wrong password. Once they hit like 5, then what I'll do is like give a message that says, okay, you've logged incorrectly 5 times. You cannot attempt to log in again for, pick a number, 5 minutes, even 1 minute, right? Something like that. But you can imagine if somebody's trying to like submit 1,000 login requests per second, having every 5 back them off by a minute or 5 minutes is a major obstacle, right? And really creates some issues there. And users won't mind that too much because, if they get 5 wrong in a row and then you tell them they have to wait like 3 or 4 minutes, they'll be okay with that because like, yeah, and maybe give them a phone number to call or some other thing. But just doing a little bit here can make a huge difference, right? As far as from a security point of view, right? And then of course record these failed login attempts so this kind of stuff is happening. So you can maybe take some additional action or change some stuff, or do some sort of a combination of the two, right? Like every 5 login attempts, delay them for 5 minutes. But if it's more than like 20 or something, then lock them out because something really bad is happening at that point. Something, right? But you get to pick the balance. But feel free to be creative, right? And just find that happy. And it depends on your users and your application, right? Users tend to be much, much more tolerant about these sorts of things if it's a site that is holding valuable information like their bank or something, right? But they tend to be less tolerant about things like this if it's, something they don't care about, like some sort of social sharing site or something or whatever, right? So find the balance, okay? Cool. So we'll talk about more, but these are just some basic sort of good practices with modern sort of authentication, right? Okay, so let's talk about some authentication protocols, right? Some mechanisms we can use in a HTTP-based application. So it could be a website, it could be a web service. But some different mechanisms we can use for performing authentication. Now, one thing I want to make sure that you're clear about is that the mechanism or protocol that we use is separate from the back-end credential store that we're actually authenticating against, okay? So don't let one sort of drive your decision about the other. What I mean by that is, some people, they'll say, well, we need to authenticate against Active Directory accounts, so we're going to use Windows-based authentication. You can do that, but you could also use HTTP basic authentication to gather the username and password, and then still, once you have that, authenticate against Active Directory accounts, right? So the mechanism that you use for actually sort of enabling the authentication is totally separate from what you actually authenticate against the backside. So I can use basic authentication, authenticate against Windows. I could use token-based authentication to authenticate against Active Directory or some sort of OAuth-based system, or these two can vary independently of each other, right? And we'll talk about, what would make you pick one of these versus another, okay? So the first mechanism we have is one that's actually built into the HTTP protocol, which is HTTP basic authentication, okay? There's only a couple that are actually defined by the protocol, and this is one of them. Now, what I tend to find as I sort of travel around different places is that I end up going a lot of places where they've got some sort of application, and based on their requirements, HTTP basic authentication would actually work beautifully, but then they don't tend to use it. And so I'll ask them, why aren't you just using HTTP basic authentication for this? And they'll say, well, we can't use basic authentication, right? Why not? Because it has the word basic in the title? Or what? Huh? Now, in some other cases, this doesn't fit the bill, right? And you need to choose something different. However, in some cases, HTTP basic authentication can work great. So, well, how does it work? And then, why am I sort of a fan of basic authentication? So, first of all, the how it works part. What's going to happen here is that it's very simple, right? The client sends, as part of the request, a header that includes the username and password, right? The identifier and the credential. It's sent in a header with the request. Now, because the credential is being sent in the header of the request, you should immediately think, okay, well, I have to make sure nobody can read that, so I have to be doing this over HTTPS. So yes, if you're doing basic authentication, it has to happen over HTTPS because the channel has to be secure, so the credential is not compromised, right? Okay, cool. Now, the way it works is it's this challenge-based authentication scheme. So somebody goes to make a request, and here's where this works really well is, well, it works really well for web services, but let's talk about just a regular website first. So let's say I have a website, I go into IIS, and I just turn on basic authentication for my website. Boom, right? Okay, so now somebody makes a request to my website in the browser, and just a regular old request. Now, because I have basic authentication turned on, the web server is going to return a response that includes a 401 status code, which is unauthorized, and includes the www authenticate header, and it specifies, in this case, basic. So in other words, the server saying, nope, you are not authorized to get that resource, but I am willing to accept basic as the form of authentication. Sweet. So it's the client's job at that point to obtain the identifier and credential of the user. Now, in the case of a web browser, the web browser would just pop up a dialog box that says type in your username and password. Okay. They click the button, and then what they do on the next request, the browser will send the username and password in a header for the next request, and every request that follows. So during that sort of session, the browser is sending that information within the header of every request to that domain. Okay. And so the credential and identifier is being sent with every single request. Now, I don't care for this for a website, one that has sort of a visual, it's HTML. And the reason I don't is because I don't have enough control over the experience for when they log in. So in other words, they get this, the dialog pops up, but that dialog is being popped up by the web browser, and so I have no control over what that looks like and the behavior, and so I'm not a fan. However, I do like basic authentication for securing web services, okay? And it actually works very, very well for that. So I go ahead and build a web service, right? So I use like ASP.NET Web API or whatever. I build my web service. It's got lots of different API methods, endpoints, right? Methods that I can call to get data. And then I just enable basic authentication. So what that means is if you want to call any one of these methods in my web service, the request that you make has to include in the header the username and password. And because it's over HTTPS, it's fine, it's secure, but the main reason I like it is it's dead simple to implement. So what that means is if I build a web service and now you're building clients that are going to talk to my web service, you're building websites, you're building iPhone apps, Android apps, thick client, Windows apps, whatever, and then you say, hey, I want to call your web service, I'm building an Android app. How do I talk to your service because it requires authentication? And then I say, oh, well, it's HTTP basic authentication. As an Android developer, your response is probably going to be, oh, shit, I can do that, easy, right? And in most cases, that's sufficient, right? I mean, it's totally up to you to decide what the credential and password, what the username and password are going to be that get sent, so you can, make determinations about that. And in the case of something like an Android or an iOS app, it's up to the developer of the app to decide how to gather those credentials from the user. So they pop up something like some sort of box, whatever it is, and the user puts in their information, or maybe you integrate with like Face ID on the iPhone or whatever it is. And then once you've determined that the user's good to go, then you decide what username and password to send in the header when you call the web service as part of that authentication, okay? And so for the last 10 or 15 web services that I built, probably 12 of them have just used basic authentication as their form of authentication because it meets all the requirements, it's super easy to implement, okay? And what do we end up actually authenticating against on the back side? Doesn't matter, whatever. The username and password come in, so now you talk to whatever you need to talk to, your database, Active Directory, I don't care, right? To figure out if that identifier and credential are valid, okay? So, but I use basic as the mechanism, the protocol, right? So bottom line, don't discard it right off the bat, right? Give it a chance and see if maybe this might meet your requirements and you can keep your architecture really simple, right? Okay, but there are some times it's not going to meet your requirements, and that happens, that's fine, okay? So what are some other options? Well, another option that we have is another one that's defined by the HTTP protocol, which is digest authentication. Now, the idea with digest authentication is that this was developed as a way to do HTTP basic authentication without having to require HTTPS. In other words, without sending the credential in clear text as part of the request. How do they do that? Well, there's a bunch of other little details and bits that go into this, but the key piece here is that instead of sending the username and password in clear text, we're sending an MD5 hash of the username and password, okay? So if somebody was to intercept that, they don't have the credential of the user. Now, the bad news with this though is weaknesses have been discovered with the MD5 hash algorithm when used in security roles like this. And so generally the industry recommendation now is to never use digest authentication unless you're actually using it over HTTPS because of those weaknesses in the hash algorithm. Now, what that means is, well, wait a minute. If the whole reason for doing this is so I can do authentication over HTTP without HTTPS, but now you're telling me I have to use HTTPS, why would I use this instead of basic? And there's really no good reason, okay? There's no benefits to this over basic authentication if you're doing them both over HTTPS. And basic authentication is much simpler to implement both on the server side and the client side. So pretty much don't use digest authentication. No reason to. Just complicates your life for no benefit, okay? If you're comparing this with basic, okay? Cool. Now, I mentioned that I would throw out some additional sort of recommendations in terms of books and things. And so there is one I want to throw out there now, because this is just a good time to mention it, is really, really good one. It's called Pro ASP.NET Web API Security, okay? Has many stars. Really good material in here, especially if you're looking to build services and you want to think about what your options are for securing those services. And so one of the chapters in this book, the author does a really good job of showing you how you can actually implement HTTP basic authentication totally, completely from scratch, just in code, without turning anything on in IIS or in the web server, but just doing it all programmatically, right? And it really helps you to understand how basic really works. It's really cool. It even has a chapter where he does digest authentication from scratch, which is a little bit more tricky and involved, but also kind of cool to sort of learn. But the other thing is this book also has really good coverage of things like HTTP anatomy and security. So talking about just more about how the HTTP protocol works, things like entity tags and cross-origin resource sharing and things like that. And then encryption and signing. So talking about symmetric encryption versus asymmetric encryption, and hashing and HMAX, and all those sorts of things. And so it's good stuff, right? And then gets into talking about ownership factors and web tokens and OAuth, which we're going to talk about a little bit today. Really, really solid material, right? And again, the title of the book is Pro AWeber API Security, but probably 80% of this book is just really good general security stuff. And then 20% is specific just to building web APIs. Client certificate-based authentication. This is one that does give us something beyond what HTTP Basic could provide. And in this case, what client certificate auth provides is sort of reverse authenticity. What I mean by that is, when we were talking about HTTPS the other day, when you go to a server like bankofamerica.com and you start to establish the secure connection, part of establishing the secure connection is that the server sends to you a certificate. The client receives that certificate, and then they're able to verify the authenticity of this entity because they can check that the certificate has been issued by a trusted third party, right? So we have this other third party that we trust, and because we trust them, and because they trust them, I can therefore trust them, right? Because this third party is involved, okay? Client certificate-based auth basically means that when the client goes to authenticate against the server during this handshake process of establishing the secure connection, the server provides a certificate to the client, but then the client provides a certificate to the server. So the client says, hey server, here's a certificate that says who I am, signed by some trusted third party. So now the server can actually say, oh, cool, now I have additional assurance that you really are who you're claiming to be because of this trusted third party again. So we get the same thing that we get for servers for clients. Now that sounds really cool, right? So we get like mutual authenticity. The downside to client-based auth, client certificate-based auth is every client that talks to my service has to have a certificate issued to it that it can send when it goes to establish the connection. So just like you have to sort of, go obtain a certificate for your server and pay somebody some money and install the certificate and now that has to happen on the client. Ugh. So this can work very well if your environment is basically some sort of service and then you have complete total control over the clients that are out there that are going to talk to your service. So one real world example of this is I had a client one time that was a major retailer in the US. And what they would do is they would set up these point of sale devices, which is basically a PC-based device that they would install some software on and everything. And when they set it all up, they install a client certificate onto that point of sale device. And so then when they push these point of sale devices out into their different stores all over the country, these devices are basically kind of like phoning home to basically tell the headquarters, what's going on and what's being sold and all these other things. But they want to make sure the communication between these two things is secure. But because they have total control over all these clients, they can install these client certificates on all these clients, bake them right in there, right, when they set them up. And so now when the call is made, they've got some stronger authentication between server and client. It's transparent to the user of the point of sale device. They don't see this happening behind the scenes, but this ensures that things are nice and good. And then if one of these point of sale devices gets compromised or stolen or something, the people back at headquarters can revoke that certificate. So when somebody tries to establish a connection, they can see that certificate's been revoked, and but it's not just using a password. In other words, this is a ownership factor. It's a certificate that's installed on these devices versus a knowledge factor, which would just be some sort of password or something that somebody on the street could guess or potentially come across. So, but there's definitely some administrative overhead and hassle involved with this, and it doesn't really work well if you're trying to build an application that you're making available just to like people out on the internet, because you're not going to buy them certificates and have them installed on their machine and all these kinds of things, okay? But if I have kind of a closed system where I want sort of, maximum trust between the two parties, client certificate-based auth could be an option. Now, even though each certificate is unique for each client, on the back side, they end up all mapping to the same account on the back side. So on the server side, you basically have one Windows account called POS device. And even though all the certificates are different, they all map to that same backend Windows account to make the backend administration easier. But that way, each certificate can be revoked individually. Because if I just put the same certificate on every device, then how would I sort of revoke access to just one of them? It would be difficult. So yeah, okay. Now, in a lot of cases, people will go to this kind of solution. It tends to be overkill. They don't really have the need for that. There's other ways we can do it, which we're going to talk about here in a few minutes. But it is an option. It's out there, so something you can look more into. Another option that's out there, which also works very, very well, is something called a pre-shared key authentication. All right, pre-shared key or API key, some sort of secret that is shared between two parties out of band prior to usage. Okay, we'll talk about that. Transport security is required to protect the key. So this whole thing's happening over HTTPS, fine. The pre-shared key itself is typically some big, huge, large base64 encoded string, some just big like, bleh, okay? So we're gonna actually consider this an ownership factor because of that. Examples of where this kind of authentication system is used, Amazon Web Services, Windows Azure, okay? And so because these guys are using this kind of a system, if you use this kind of system for your services and things, it kind of provides you a sort of an easy way to argue that you're doing it right. Because when the boss says, "Oh, we're using this pre-shared key system. How do you know this is the right way to do this?" Well, it's what AWS uses. Oh, okay, cool. It gives them a little warm fuzzy, right? Because it's what the big boys use. So, what does this kind of stuff look like? So, I'm logged into my AWS account right here, okay? And so I go into security credentials and I go down here. And so basically AWS has a big collection of services you can call, APIs, right? So I can call the AWS API and create a new VM or launch a new load balancer or whatever. So if I want to write an application that calls these services, I want to make sure that it has a way to authenticate me. So they use a pre-shared key style system. So what I do here is I log into my control panel and I go ahead and create a new access key. So I have a button here that says create access key and I click on this, bloop, bloop, right? And what it does, it basically generates two big giant chunks of stuff, right? One is my access key ID and the other is my my secret key, right? There's another big chunk of stuff, okay? Now, once those two things are generated, I have the opportunity at the time I generate them to download them. Right, this is me exchanging this information out of band because it's not part of my actual usage of the API. This is me using their control panel here. And so I generate my keys, I download them to my machine, cool. Now what I do is I take my access key and my secret ID and I bake them into my client, like my web app. So I put them in my web apps, web config file or app settings or whatever. And because that's the thing that's gonna call Amazon Web Services. Okay, so now when I go to craft a message, when I go to call the web API, the service, I'm going to include in that message that I'm sending to the service my access key ID because that serves as my identifier. I'm not going to send the secret ID as part of the request, but the secret ID is used for other things. So for example, I'm going to use the secret ID to digitally sign my message, okay, to sign my request. So now when I send the message to AWS, AWS receives a message. It'll say, oh, well, it looks like this message is coming from the user that has this access key ID. So now I know who it is. And now I need to make sure this is a legitimate request. Now I have a secret key and Amazon has my secret key, but the secret key is not sent with the message, right? Instead, what Amazon does is they'll basically take the message that's being sent and they will generate an encrypted hash basically of the rest of the stuff that's in the message using my secret key and compare it to the signature that I sent with the message. So it's just a way that they can verify that, okay, this was really sent by this particular user because they're the only user that could have generated this signature because they're the only user that has that secret key. Now, of course, Amazon, they have the secret key too, so they can verify it, okay? This is basically, they use the access key as the ID, and they use the secret key to provide a way to prove that I sent the message. and also to verify that the message has not been modified in any way. Because if anybody modifies the message in transit, then the digital signature won't verify anymore, right? Now, the person who modified the message, if they try to generate a new signature, well, they can't because they don't have the secret key that was used to generate the signature, right? So it ensures that the message is authentic and has not been modified, integrity, right? And again, if you want to sort of dig into more depth of how all this works, just go look at the AWS documentation that explains how their API works and how their authentication works. And then you can implement a system that works very similarly, right? It's actually not difficult at all. And now I am going to show a couple examples though of how you can sort of roll your own system that does something like this, okay? This is referred to as a pre-shared key type system. And again, on the back side, this is just the mechanism, right? On the back side, you do whatever you need to do. So once you've verified that the message is authentic and hasn't been modified, well then you can, check what permissions this particular user has, or whether or not they're allowed to call that particular thing, or whatever you need to do, right? Once you've established the identity of the user. Notice with basic authentication does not provide any protections around whether the thing that we are receiving, the request that we are receiving, has been tampered with or modified, right? There's no way to detect that sort of thing, right? Now, you could use basic authentication and still implement sort of a digital signature as part of what you're sending, but you'd have to bolt that on sort of yourself or something, right? So pre-shared keys type system or an API system. Now, to pull this together a little bit, I'm going to walk you through an actual real world application that I helped to develop where I used a pre-shared key type system, okay? So I mentioned in this slide, I say must consider the possibility of a replay attack maybe, okay? It depends on the app. So let me walk you through a little case study here, okay? So I had a client, and the client's business was that they manufactured these printers that were used in Ester environments. So in other words, printers that would be used on like flight lines or in combat zones, things like that, really heavy duty, high strength printers. These printers also had network cards built into them because they were network enabled printers. So when they were being manufactured, a MAC address would be assigned to the printer because it's a network enabled printer, right? These printers were being manufactured in 3 locations: China, California, and Chicago, Illinois, okay? 3 different manufacturing lines. And so they had to develop a way to assign MAC addresses to these printers because basically the organization receives sort of a range or a block of MAC addresses that they can use for their devices because every manufacturer has to make sure they don't collide with each other, that MAC addresses are all unique. Well, the system that they were using was written in Visual Basic, had a Microsoft Access database, and just was not implemented very well. And so what ended up happening is they had an occasion where they manufactured a couple dozen printers that all had the exact same MAC address. Oops. When I was explaining this to my parents at one point, they didn't really understand, like, well, is that really a big deal? And I said to them, I was like, well, imagine if, Ford Motor Company just manufactured and shipped 300 pickup trucks that all had the same VIN. And they were kind of like, oh, I'm like, yeah. So anyway, so this happened. And then a few months went by, and then it happened again. Now, when it happened the second time, it got them in a little bit of trouble. And so I think it's the FCC or whoever was basically saying, hey, you need to get your house in order because if this keeps happening, you're going to basically revoke your right to have MAC addresses that you can issue like this, or you're going to get fined, or all sorts of bad things are going to happen. So they said, all right, we need to come up with a replacement system. So this is where I ended up getting involved. And so how would you implement such a system? Well, here's what we could do, right? We could go ahead and build a web service. So we have a server sitting in Chicago because that's like the headquarters, and it's going to have a web service on it exposed to the internet, and it's going to be the almighty issuer of MAC addresses, right? So the service is going to sit here. It's got like a big database table full of MAC addresses, and then anytime anybody needs a MAC address, like say the manufacturing line in China, it'll make a call to the web service, whoop, says give me MAC address. The web service will grab one from the database, mark it as used, and then send the MAC address back to the caller, to the client, right? And the client will use that and assign it to the printer. Then in California, whoop, same thing. And in Chicago, same thing. Okay, there's a few issues we need to deal with, okay? Issue number one is that these internet links especially the one from China, are not super reliable, and they could have a lot of latency involved in them and things like that. So, okay, that's an easy problem to solve. What we're going to do is when you call the web service, instead of returning one MAC address, we'll return like a block of 50 or something. Okay, so you call the web service, we give you back 50 MAC addresses, and then you can then use those locally, right, and hand them out. And when you start getting low, like you only got 10 left, you'll make another call to the service, get 50 more, right? And then there'll probably be some back channel where we're sending back logging messages that says we're, which ones we're using or whatever. Fine, okay. So we solved that problem. But then there comes the next problem, which is authentication, which is I don't want this web service to just be callable by anybody anywhere, all right? Okay, so first, we only make the service available via HTTPS, great. Next thing is, how do we do authentication? Well, I'm gonna use a pre-shared key type system because really here, I only have 3 clients. I have the machine that's sitting in Chicago, the machine that's sitting in California, the machine that's sitting in China. So because I only have 3 clients, what I'm gonna do is I'm just gonna generate 3 pre-shared keys. Basically this big, huge chunk of stuff right here, right? Okay. I'm gonna give one to the machine in China, one to the one in California, one to the one in Chicago. This pre-shared key acts as both the identifier and the credential. Super simple form of authentication. Basically, when a request is made to the web service, if this header is present and it includes a valid value for this pre-shared key, then you're valid and I know who you are because I have a list of the 3 that are valid, right? Fine, and it's over HTTPS, so nobody can intercept it, read it, I'm happy, okay? But then comes the next part, and I'll rotate these keys from time to time, right? So the next part is, okay, so it's HTTPS, so nobody could read the data going back and forth. So nobody could obtain one of these MAC addresses, for example. Nobody can call the service because nobody has a valid pre-shared key. And they can't read one from an existing communication because it's all encrypted HTTPS. And they probably can't guess because that's gonna be really hard to guess. What about a replay? So what if somebody was able to sort of obtain one of these messages and they can't read it, they can't really modify it, but what if they just resend it to the server? What would happen? Well, in our case, because the server is sort of, using up resources, each time it's called, it gives out 50 MAC addresses and marks them as used. If somebody was to send the same message a second time, potentially we would just use up 50 more addresses. Now, again, depending on your application, this may be a concern, it may not be. But in our case, this was a concern. So how can we prevent something like a replay attack, right? Which is somebody just resending the same message, right? Well, we got a few options, right? Option number 1, we could use something like a timestamp. So basically, when the client goes and sends the message, it includes a header with some sort of date time value. And the server says, well, if the date time is older than some certain amount of time, then I will consider that message invalid and won't process it. Yeah, but how tight of a window are you going to choose there? And how is that? And then what about the clock of the server versus the clock of the client? Are they synchronized? Or there, there's potential issues there? And so it could work maybe, but not ideal. So what's another option? Well, maybe we use something like a counter. So there's some sort of incrementing counter value on the server. So when it receives a message, it has a counter value of say 33 here. And so it checks to make sure that counter value is higher than the last counter value that the server knows about, okay? If it's not, then that's probably a message that's been sent previously and we'll reject it. Problem with that is it requires a little bit of coordination because you've got, China and California and Chicago, and so they all got to kind of keep track of, well, what's the current counter value and how am I going to, so that could potentially work as well, but also a little cumbersome. So what about a third option? Oh, and by the way, notice these are just HTTP header values. So these are custom header values that my client is just, adding to the request, and then I'm just reading them at the server level. And notice they all start with X dash because when you're adding your own custom HTTP headers, it is generally best practice to start them with X dash just to make sure you don't pick a header value that's going to collide with one of the predefined headers or one that maybe gets added later. So we use the X dash as just convention, okay? Okay, so what's another option we could use? How about if we do something like a message ID? And what we're going to do is we're going to use GUIDs, globally unique IDs, right? Now, I asked the group this morning, I said, does anybody know how GUIDs are generated? Math. Yeah, so there are a couple different variants of the algorithm used for generating GUIDs. They're real easy to get in .NET, right? You just do like GUID.NewGUID. The initial way that these were done was that when you ask the system for a new GUID, it would start with the MAC address on the system, which is supposed to be unique to that machine, unless you're using one of these printers that was, yeah. And then it takes the current system date time down to a, as accurate as it can get, and then it combines that with a chunk of random data. So if you've got one machine over here that generates a new GUID, and then you want to generate a second GUID that ends up being the same as the first one, it would have to be generated on the same machine, the same MAC address, at the exact same time, down to potentially like 100 nanoseconds or something, and get the same random data. And so the chances of that happening, right? So you can pretty much, for most applications, trust them to be globally unique, okay? One time I had somebody in class ask me, it's like, well, how many are there? And we're gonna run out? And we did some math and it was like, no, we're good. Okay, so in this case, I said, well, how about this? How about if the client, when it goes to send a message to the server to get some MAC addresses, includes as part of the message a message ID, a globally unique ID generated on the client. So it generates a GUID and sends that along with the message, and that becomes the ID of the message. So then the server's job is, when it receives a message, check to see, have I already processed a message with this ID? If I have, then throw this one away. If I haven't, then go ahead and process it. Anybody see a problem with that? Well, the server is going to have to keep a list of like every message ID that it's ever processed, because GUIDs are not sequential, they're just totally random. So it's going to get slower and slower and slower over time to basically consult this list of previously processed message IDs. So, this has potential, but I'm going to have to add something to it. Okay, so how about this? And this is what we ended up doing. The first thing I did is I went to the service, the web service, and I added a new API endpoint called getServerTime. So this is just some method you can call that returns the current time of the server, because that's going to come in handy in a second. Now, what I ended up doing is once I did that once, now every single time I build any web service, the first thing I do is I just add a method that returns the current server time, because that acts as sort of an application level ping, like a health check. Because sometimes, you get that question, right? Somebody's like, hey, the app doesn't work. I tried to use the app, I can't reach it. Well, can you ping the machine? That's usually what your network guy always asks, right? Well, in this case, that web service call acts as sort of an application level ping, one that's not just seeing if the machine is alive, but is my application actually functioning, right? And it doesn't even have to have any authentication around it, because I don't care if anybody can call it, whatever. It's just super handy to have. Maybe don't call it getServerTime, call it like XF317256 or something, because I don't want people just finding it by accident, but if they do, I don't care. Okay, so I have that getServerTime method. So then how does it work? Well, what the client will do, like in China, is I need to get some more MAC addresses. Cool, all right, so I need to create a request, which I'm going to send to the web service. So I go ahead and create this request, HTTP request. I include my pre-shared key. I call the getServerTime method, get back a time, include that as a timestamp header with the server time that I just received, generate a message ID, which is that GUID, and include the message ID in there, and then send that to the server. Server receives the incoming message, and the first thing the server does is it looks at that timestamp header, and it says, is that timestamp header older than, pick a number, 30 minutes, okay? If it's older than 30 minutes, throw it away. If it's not older than 30 minutes, take the message ID and compare it to the list of message IDs that we've already processed. But I only need to keep 30 minutes worth, because the first thing I did is if it's older than 30 minutes, I just throw it away. If it's newer than 30 minutes, then I consult the list that I've kept. Now, once I've consulted my list, I'm like, yes, I've not processed this before, sweet, add it to the table, and then delete ones that are older than 30 minutes, right? And then send a response, okay? So the reason I wanted to kind of go through this is not sort of a defined pattern or sort of documented way of doing this. This is just us thinking about what were the requirements of the application and how can we come up with something that's going to meet the requirements but isn't overly crazily complicated, right? It's as simple as we can make it, but still meet those requirements. So our requirement was avoid a replay attack. But when we started thinking about how to do it, some ways involved too much complexity that we wanted to have to deal with, and other ways had an impact on performance, like the message ID list. And so we tried to find that balance, okay? And so, feel free to be creative when you're building something like this to think about, how do we want to do our authentication that keeps it simple, but can sort of meet some of these requirements we have, like to avoid something like a replay attack. And that's fine. As long as you're using sort of good algorithms and good fundamentals, it's okay to kind of be a little bit creative. Okay, there was one other thing I'm going to add to this, which is you notice this header on the bottom here, this X. By the way, this example on the slide, I have both counter and timestamp. That's not the way the system actually is. I just put them in there to show you so I could talk about the different options and choices, right? But the actual application does include this last header, which is this X-signature header, okay? Because I'm going to add one more requirement to this application. So I want it to be confidential. I don't want people to see the data going back and forth, HTTPS. I want to have a way to prevent like replay attacks like we just talked about, but I also want to have integrity. In other words, I want to have a way so the server can verify that the message didn't get corrupted or modified in transit. Because while it's traveling across the world, nobody can read it. Nobody could potentially like maybe now replay it. But what if somebody just messes with some of the bits, right, and screws it up? And if they get lucky, then maybe bad things could happen. So to achieve that requirement or that feature, what we did is we just added another header called X-signature. And all we did is we basically took generated an HMAC, which is kind of an encrypted hash, if you like, of all the other fields in the message, okay, and included it here. So what the server could do then is regenerate that HMAC on the server to make sure that everything matches up and nothing got messed with or modified, okay? An HMAC is basically you're just generating a hash, but you're also using a secret key to generate that hash. So both the client and the server have the same secret key that was shared out of band previously. That's like the secret ID in the AWS example. So both sides can generate a HMAC of all the other fields using the secret key. And so when the server does that and then compares it to the value here, they should match. Yeah, the PSK is just acting as like, think of it as just username. Yeah, that's all it's really acting. I mean, it's acting as both the username and the password in this example. So it's the identifier and the credential. But yes, this key, this that's generated here is an additional key that both sides have that's not included in the message. SHA-256, yeah, which is typically fine. SHA-256, when we talk about hashing algorithms, there's several different choices available. And actually, you know what I want to do for you guys? Since we're getting a little bit into the crypto stuff, I'll give you a little bit of bonus material here. So this is the, I got some slides here actually from the full like 4-day security class. And so in there, one of the things we talk about is different sort of cryptographic topics. And so when we're talking about encryption, this is where we are encrypting something and then later on we can decrypt it. So it's reversible, right? And so if you need to store some sensitive data in encrypted form and you need to be able to reverse that and get the data back, we'll typically use symmetric encryption. And in .NET, we've got several different algorithms to pick from for doing symmetric encryption. We have RC2, DES, triple DES, and AES, which is the Advanced Encryption Standard. Uses the Rijndael algorithm. Depending on the key size that you select, the US government considers AES good enough for stuff up to the secret level, and all the way up to top secret if you choose a key size of 192 or 256 bits. So generally, the short answer best practice here is if you need to do symmetric encryption in .NET, use AES. Bang, okay? Rijndael. Yeah, that's the name of the algorithm, but the class that you use in .NET is actually called the Rijndael managed class. Now, AES, the Advanced Encryption Standard, is a specification developed by the National Institute for Standards and Technology, and the Advanced Encryption Standard says you need to use the Rijndael algorithm with a key size of at least 128 bits, okay? If you use the Rijndael algorithm and your key size is less than 128 bits, it's not AES anymore, okay? So it's a fine point, but there's two different things, right? So people, when they say, hey, you should use AES, okay, well, depending on which key size you use with the Rijndael algorithm, it'll either be AES compliant or not. So these other algorithms, by the way, these other symmetric algorithms, typically, we don't bother with these. So RC2 is considered weak, shouldn't be used. DES is not really considered suitable for today's needs. Triple DES is still considered okay, and NIST says it's probably sufficient up through, like, they guess like 2030, when brute force attacks may become feasible. But because we have this one and the performance is almost identical, you might as well use that one. And if you go to 192 bits, you know, that's good enough for US government top secret, so you're probably fine, okay? Now, when generating a symmetric encryption key, so let's say I want to do symmetric encryption, I decide to use AES, so I'm going to use the Raindow managed class for the 192-bit key. Fine. So now I got to generate the key. The key needs to be as random as you can make it. Now, in .NET, we have some classes that, there's a class just called random, and that's great for creating like card games and stuff. But if you want to generate random numbers that are sufficient for cryptographic uses, there's a different class you use, and it's the RNG crypto service provider for generating random numbers, basically as good as you can get. There's only so much you can do on a computer without some sort of external source. If you would ever look at like the guys that make like online poker and stuff like that, they actually use hardware which is external to the system, like the levels of noise from the local electrical grid and things like that to generate truly random stuff, because a computer is just not capable of generating something that's actually truly random. So you need something external. But anyway, in .NET, this is considered sufficient, and so we want to make sure we're using the right class. And then in addition to a secret key, a separate random initialization vector should also be used. All right, so the question was asked, what's the deal? Okay, well, when we talk about a symmetric encryption algorithm like Raindow, you can think of the chunk of bytes that you want to encrypt. And what happens is that the encryption algorithm sort of works its way through this sort of sequence of bytes. And as it's working its way through this sequence of bytes and doing the encryption, say we're on this byte here in the middle. Well, it's going to encrypt that byte, but it's also going to use some information from the previous byte as part of the encryption of this current byte, right? So it's using the key, but it's also using information from sort of the previous byte. And this is, they do this to kind of prevent certain kinds of patterns from appearing in the ciphertext. However, there's an issue, because if we go all the way back to the beginning of the byte stream, and I go to encrypt that first byte, there is no previous byte to use. And that's the purpose the initialization vector serves, is it's some sort of random piece of information that serves as sort of that seed byte for encrypting the first byte of the stream. And then it sort of chains off the bytes from that point on. So when you go to do symmetric encryption with something like AES, you have to generate two random values, one that's going to be the key and one that's going to be the IV, or the initialization vector. And you need both of those when you do the encryption, and you need them both again when you do the decryption. But you can actually store them together. So you can generate the key and the IV and then just like mush them together with like a pipe in the middle or something or whatever, and store it as one unit. And then just break them apart when you go do the encryption and decryption, because it's making sure that the output, the ciphertext that you end up with, doesn't have sort of patterns in it that can be used, right? And so, but they don't have to be stored separately or anything. They should both be stored equally securely, but they can be stored together. Yeah, so that's kind of what that's about. But just think of it as just, you know, another part of the key, if you like. Okay, so asymmetric encryption. The idea here is that symmetric encryption tends to be very, very efficient. So when we talk about symmetric encryption, like AES, you can encrypt very, very large chunks of data in one operation, and computationally, it works very well. It's very efficient. But the problem with symmetric encryption is key management. If I want to send you a secret message and I want to encrypt it using symmetric encryption, in order for you to be able to decrypt my message, you need the secret key. So I've got the secret key, I've got the encrypted message, I'm sending you the encrypted message, but how do I give you the key, right? You need the key somehow. So in the case of the US military, it used to be that when we wanted to send messages from like Washington, DC over to Europe, we did it with symmetric encryption, but in order to make the symmetric encryption happen, we literally had to have some individual with a briefcase handcuffed to his wrist, get on an airplane with the cryptographic material, travel over to Germany so that they would have the secret key, and now we can exchange messages back and forth. Okay, because key management becomes the big problem there. not the actual, security of the message. So, but if I'm want to say on the web, I want to talk to Bank of America in a secure fashion, well, we'd like to use symmetric encryption because it's very efficient and it works very well, but we both don't have the secret key, so how are we going to do this, right? Okay, so asymmetric encryption is we generate a pair of keys, mathematically linked keys, basically, okay? And one key can be used to encrypt the message, and then the other key can be used to decrypt the message. So what can happen is I generate a pair of keys, you generate a pair of keys. I choose one of my keys and I make that key public. You choose one of your keys and you make that key public. Now, if I want to send you a message, I basically grab your public key and I encrypt the message and I send it to you. And the only way that message can be decrypted is with the matching private key, which only you have. When you want to send me a message, you use my public key, encrypt the message, send it to me, I can decrypt it with my private key. The keys are the same, I just pick one to be public and one to be private, okay? Once I encrypt the message using your public key, I can't decrypt it. The only one that can decrypt it is the person with the matching private one, which is you. The problem with asymmetric encryption is it's very, very computationally intensive compared to symmetric encryption, and the size of the payload that can be encrypted with one operation is basically the same as however big the key is. So you can only encrypt very small things in one go. So if I want to send you a big message, it's hard because I could get your public key and then I can encrypt a whole bunch of the pieces of the message and send you all the pieces, then that weakens the strength of the system because of patterns and things that can occur. Now, in the case of the defense message system that I mentioned before, we used asymmetric encryption for doing this. So if General A wanted to send a message to General B, he would encrypt the message using General B's public key. But if General A wanted to send a message to 50 people, he would have to encrypt the message 50 times with each of the public keys of the recipients. The problem was the encryption was happening on these little PCMCI cards that would go inside the machine. And so when General A went to send a message to 50 people, the card would overheat and start to smoke and it created issues. So anyway, and so the way HTTPS works is it uses a hybrid scheme, sort of a combo here. And what we do is when I'm talking to Bank of America, we start off using asymmetric encryption. So basically the browser's talking to the server, and so the server has like a, I'm gonna simplify this a little bit, but it's the same deal. The server has some public key. So what the client does is it basically can send a small piece of information to the server encrypted using the server's public key, so the server can then decrypt it using the server's private key. So what's that small piece of information that we send? A symmetric encryption key. So we use asymmetric encryption just to exchange a symmetric key, and now the whole rest of the communication can happen via just regular AES symmetric encryption, right? And so as we talk about this like hybrid scheme, okay? And that works extraordinarily well to just use asymmetric encryption to exchange the key. We couldn't do that in DMS because the defense message system is not sort of a real-time back and forth communication like HTTPS is. You craft the message, you send the message on its way, and then it could take days, hours, or whatever to get to the destination because it could get routed through all different places and stuff. And so, we had to just use straight up asymmetric encryption. So yeah, but that's different than our digital signature that we're talking about, okay? So when we talk about hashing functions, so this is where we get to where I wanted to talk about, which is we've got different hash. Now, what's a hashing function, first of all? A hashing function is just some sort of function that maps digital data of an arbitrary size to digital data of a fixed size. So in other words, if I'm using a hashing function, I could give it 10 megabytes of stuff, but it's only going to spit out like a 512-bit value, right? No matter what size of stuff I feed in, it always spits out the same size output, okay? And it's a cryptographic hash function is one that's considered it practically impossible to invert. So you can't go the other way, right? You can't take a hash and turn it back into its original source data. But this is useful for something like passwords because we just hash the password and compare it to the hash we have. We don't need to know what the original was. But this is different than encryption, right? Because this is hash function is one way. Now, there are different hash functions that are available in .NET. MD5 is one, but there were flaws that were discovered in that around collisions, and so we aren't supposed to use that for cryptographic tasks. There's SHA-1, which produces a 160-bit hash value, but in 2005, we've got some attacks that were discovered that that might not be secure for additional use. And then we have SHA-2. So no weaknesses discovered yet. And when the question was asked which hashing algorithm we used, it was SHA-256, which is one variant of SHA-2. We also have SHA-384 and 512. Just bigger hash values that are produced, a little more heavy on the CPU, but not too bad. And then we have SHA-3, which is the newer one that you can get via a third-party library, but is not built into the .NET framework as of yet. So then we add one more bit to this, which is when you generate a hash, when I showed the message with the signature header, I can't just take a hash and stick it into that header, because then some evildoer could basically modify the message and then just generate a new hash and stick it in there. So that's not good, okay? So yes, if I've got a message and then I generate a hash and include the hash, then somebody else could regenerate the hash from the message and make sure the hashes match, but I have to have a way to make sure that somebody evil can't replace the hash with a new one. Now, depending on your needs, that may not be a concern. So how does like GitHub know what's changed? So if I have a big, huge collection of files and then I, click sync, how it detects which things have changed and which things haven't changed is by using hashing, right? So it takes a hash of all the files and then a hash of all those and a hash of hashes and a hash of hashes to figure out sort of where in the tree stuff has changed, right? Just by using these little hash values. But in our case, with sending a message, I want to make sure the hash can't be regenerated. And so we use something called a keyed hash message authentication code, right? And so basically this is a hash function that's used in combination with a secret key. So when I call the hash function, I give it the thing I want to hash as well as a secret key. So you can kind of think of it as like an encrypted hash if you want, right? And an HMAC can be used to check the integrity and authenticity of a payload, because if the receiver generates a new hash using the same secret key, then I know that one, the message hasn't been messed with because the hashes match up, and two, nobody was able to generate a fake one because the sender has the secret key and I have the secret key, nobody else does, and the secret key was not sent as part of the message. Digital signature. That's basically the definition of sort of a digital signature. Now, we could combine, I don't want to go too far here, but we can combine this with asymmetric encryption, because I mentioned those public-private key pairs. So in the case of the defense message system, I'll use it again. I'm General A, you're General B. I want to send a message to you, and when you get it, I want you to be ensured of confidentiality, that nobody was able to read the message, integrity, nobody was able to modify the message, and authenticity, that you have a way to prove the message came from me. So I want all three of those in place, okay? So how do we achieve that? Well, you have a public-private key, I have a public and private key, okay? I write up my message. Some secret stuff is going down tomorrow at 2 p.m. in the town square. Okay. First thing I do is I encrypt that message using your public key. So now I have an encrypted chunk of bytes that was encrypted using your public key. Then I generate a hash of the message using my private key, okay? So an HMAC using my private key, and I attach that to the message. And then I send it on to you. You get it. You decrypt the message using your private key because it was encrypted using your public key. So that's the confidentiality part, because nobody else could read it, because nobody else can decrypt it. Next comes the integrity and the authenticity. There's a digital signature included that says it comes from General A. So what you do is you hash the message using my public key, right? And you can check to make sure that things actually match up. I put a little extra things in there, but we can combine. And the coolest thing about that is, well, what if you don't have my public key? Well, I can actually include my public key with the message. So I can encrypt the message using your public key, send it to you, include an HMAC using my private key, and actually send my public key with the message, okay, that you can use to sort of verify the digital signature, right? Because you can verify the signature, but you know that nobody else was able to generate that key, because the only way that it was going to work with my public key is if it was encrypted using my private key. Now, you may have got lost somewhere along the way there, but it's all just a matter of taking all these little bits and combining them together in interesting ways to achieve certain features: confidentiality, integrity, authenticity, right? You may not be building some sort of messaging-based system, but if you think about something like a web service, message-based system, because you have clients sending messages to servers. So what are your requirements you need for this communication? And what kinds of different cryptographic things do you want to use to give you the features you need? So in our case, yeah, there's a little more there. So in our case of this MAC addresses for printers, we use a very, very, very simple form of authentication, which is when it comes in the door, you just got to make sure it has a PSK that we know about, and we know who that is. But when we wanted to add that integrity part, we just have the client generate a HMAC using a secret key, and then the server just regenerated that HMAC using the same secret key, and if they match, we know the message hasn't been tampered with, right? And the whole thing's over HTTPS, so nobody can read it when it's in transit. Basic authentication is great. A pre-shared key type system is still pretty simple to implement. It can work great, but there might be a case where we want to move to something a little bit fancier, okay? And this takes us down the road toward implementing something we're going to call a token-based authentication system. All right, so what's the deal with a token-based system? Well, here's the thing. When I talked about HTTP basic authentication, or even the pre-shared key system, when the request comes into the server has to take that credential, take that identifier, and then it has to match it up with some back-end credential store to figure out, okay, who does this belong to, and are they valid? You know, validate the password if it's there or whatever, and then what permissions does this user have? Are they an admin? Are they a power user? You know, what department do they belong to? There's all sorts of work that may have to be done to sort of validate this incoming credential information, right? And that could be expensive. Depending on your application, that could be work, right? Because if your web service is sitting here and your web service ends up having to talk over the network to like Windows Active Directory or some SQL Server database or whatever, and if I have to do this for every single incoming request, every request that's made to my web service, I've got to go hit this back-end credential store to figure out who you are and what you're allowed to do. That can get painful after a while, right? We want to keep our web services nice and scalable by keeping them, you know, sessionless or stateless. But that could involve a significant amount of work for every single request. Another thing that could be a problem is, let's say I have 5 or 6 different web applications. So this is my invoicing system, and this is my HR system, and this is my, you know, ticket reporting system, and some other system. And all of them might implement their entire authentication system on their own. So this one has a login page you go to log in. This one has some sort of login page that you log in on. This one has some sort of page you log in on. They all do their own thing. Well, that's kind of a bad thing anyway, right? Because I'm duplicating the same functionality across 5 or 6 different systems. And that just is bad, because somebody's going to make a fix to one, they're going to forget to fix it in the other one. I'm duplicating a bunch of code. This is just, it's a place I don't want to be. The other thing is, if I go and use system 1, and then I surf my way over to system 3, I have to re-log in, because this uses a totally different authentication system. So what I may want to do is sort of eliminate all of this and centralize it. So when you try to go to system 1, you get redirected over to some sort of authentication server that does the work of authenticating who you are. And now I can access system 1. But then when I want to then go access system 3, I don't have to re-authenticate. I can move from system to system to system, right? Freely, single sign-on basically, right? Without having to be re-authenticated every time. And also, each time I go to one of these systems, it doesn't have to do a whole bunch of work on the backside to talk to this auth server to figure out who you are, okay? So how can I pull that off? Well, you do something similar to what happens in the real world, okay? At the end of the day today, when I go to leave, I'm gonna get in the car, I'm gonna drive to the airport, and I'm gonna go through security. When I arrive at security, security is basically gonna say, okay, who are you? And I'm gonna provide them something that says who I am, and I'm gonna basically tell them, this says who I am, believe me, trust me, right? Now, if I just handed them a piece of paper with my name on it, they're gonna be like, what? No, okay? Now, it would be very painful if every time I went through security, security ended up having to like make a phone call and talk to somebody else to prove who I am, right? So So they're like, oh, well, this is who you're claiming to be, and you're claiming to be a U.S. citizen, but hold on, we got to go make a call to the State Department, and we'll do a video web conference here so they can confirm who you really are. It's not going to work, right? It's not scalable, okay? And it's going to make every request, every person is going to be very slow. So how is that problem solved in real life? Well, the way that problem solves in real life is when I arrive at security, I present them with a token, passport, right? Driver's license, whatever, but let's say passport. So my passport contains a collection of claims. You open up my passport and it has some things that I'm claiming about myself. This is my name, this is my country of origin, this is my birth date, so on, so on, so on. So I tell the security person, here's a list of claims. Believe them. And so then the security person says, well, why am I supposed to believe these claims? Well, the security person can believe these claims and trust these claims if they have a way to validate the authenticity of this token, that it was issued by somebody that they trust, and they can confirm that it hasn't been forged or modified. And that's what they do, right? So I give them my passport, they look at that and they go, yep, this looks like this was issued by the US State Department, and I have a way to verify that because of an RFID chip or a hologram or some other physical artifacts on here that they can check to make sure this thing hasn't been forged or modified. So because they can verify that it hasn't been forged or modified and it was issued by somebody they trust, the US State Department, then they can now believe the claims that are contained within the token without having to talk to anybody else. It works just on its own, okay, because of those features that are within it. So when we go to set up security for our web service and our applications, we can take the exact same approach, which is we can have a token-based system so that when I arrive at a web application, I can present a token. The web application can receive the token, and as long as it's able to verify the authenticity of this token, it can believe the claims that are contained within it without having to talk to anybody else. So it can believe that I'm an admin and that I have the permission to delete employees or whatever else without having to check with anything anywhere else or anybody else. That has performance implications, and I can also make it so that same token can work for across multiple different applications. Now, how do we implement such a thing, right? And so we're going to talk about that, but that's kind of the high-level idea of a token-based authentication system, is that the token is a container of claims. Who am I? What am I allowed to do? And you can stuff anything you want in there. What my nickname is, where I was born, whatever you want to pack into that thing. And everything in there can be believed and trusted, okay? As long as we have a way to verify the authenticity of the token. So we're going to have a token issuance authority, some service somewhere that has the ability to generate tokens, right? And then client applications can present this token to some sort of relaying party. So the application that it wants to talk to, and the relaying party, the application that I'd like to talk to, can verify my token, establish my identity, and believe the claims, as long as it has a way to do the same thing the security person does and validate that that token is good without having to make a call back to whoever issued the token, right? So these tokens, and we're going to take our break in just 1 second, but a token, what does a token actually look like? Well, could be a simple web token, which is basically just a bunch of key value pairs that are HTML encoded. So typically the audience, which is what application this token is good for, list of domain names, right? app1.lacounty.gov, app2.lacounty.gov, whatever. Expirations, how long the token's good for, just like a passport. Issuer, who issued the token? Maybe something like auth.lacounty.gov, basically the identity of the auth server, who issued the token. Roles, so what roles this user belongs to. Are they an admin? Are they a power user? Whatever, as much stuff as you want. And then an HMAC, right? The signature, right? To make sure this token hasn't been forged or modified. Basically, this is just taking all the other data contained within the token, taking a hash value using some sort of key. Typically, it's the public key of the issuing authority, right? Or the token could be a JSON web token. So basically, it's the exact same thing. It's just in JSON format rather than HTML encoded. The actual format of the token doesn't matter all that much. You could even make up your own thing, but usually it's either JSON web tokens tend to be the most popular format now for these sort of tokens. So what I want to do is let me jump over here for a second and show you a real world example of this in action. The Accelerate website, okay? Okay, so we have the Accelerate public website, and then we have a couple of other applications that are secure, private, right? One is the content management system that can be used for editing content on this site. The other is our internal system that our employees use for managing things like instructors and engagements and that sort of stuff. Two different systems. Now, at one point, each system did its own authentication, okay? This system did it one way, this system did it a different way. They were their own little worlds. So at one point, we decided that we wanted to eliminate that. And we wanted to move to a token-based system and centralize things. So here's what happens, okay? When I'm in the Accelerate application here and I go off to accelerate.com/CMS, I get presented with this login page and I can type in my credentials and I can sign in, and now I'm here on the website, but now I have this extra menu where I can edit things and do things, right? The other application, so this one is a different domain. It's franklin.accelerate.com. So this one, I log in with my credentials and I end up on a page, looks like this. This is our internal application where we manage things like, upcoming engagements, all the different classes we're teaching the next couple of weeks, all this kind of stuff, right? So, so how does this actually, what's happening behind the scenes here? Notice when I went to go to the CMS, I got redirected to a page. When I went to go to Franklin, I got redirected to kind of what looked like the same page. And actually it totally is, right? Because when I go here to log into try to access the CMS, I get redirected to auth.accelerate.com. It's a completely different server sitting out there, right? And notice in the query string there, it says R equals CMS. That's basically the return path. So after I successfully log in, that's where it's gonna send me back to, okay? So auth.accelerate.com, this server's job is very, very simple. This server only has one job. It is to accept usernames and passwords and spit back tokens. That's all it does, okay? So if I give an invalid username or password, it won't spit back a token, okay? But if I give a valid username and password, it generates a token and then redirects me back to the CMS. So again, what is a token? It's just a big chunk of stuff that contains who am I, what permissions do I have, blah, 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 and a signature, okay? So if I go look in the network panel here in the developer tools, and when I go ahead and submit this, I make the request to the CMS, and it redirects me to auth.accelerate.com. I'm on auth.accelerate.com, so I fill in username and password, I click submit. So that submits to the server, and then what the server does is it authenticates me, and then sends a redirect to the CMS, which is this one right here. So it redirects me to www.accelerate.com, and then includes this token, right? This is all happening over HTTPS, right? But it sends you back to the CMS. Now, the CMS's job is that when a request arrives at the website, it looks for the presence of that token. If it finds that the token is present, it validates that token. So basically what it does, it looks at the claims that are contained within that token, okay? And then it validates the signature. Validating the signature means it's basically taking a hash value using the secret key that both the auth system and this system know about. So it can verify the token has not been modified or forged or whatever. And so now the website can believe the claims that are contained within there. So it believes that, yes, you are Jason Bell. Yes, you are an admin. Everything's cool. I can now let you do whatever you want to do, okay? Without having to go check some password or do some other things, right? I can just believe it because nobody else could have generated a token like that, right? Now, if I try to go to this Franklin system, the exact same thing happens, which is I try to go here, and now because I'm already logged in, this is not as easy, but I get redirected to the auth page, I log in, it sends tokens, sends me back to the Franklin site. So in the case of where I've got lots of different applications here and my auth server over here, the auth server has one well-defined job, which is look at credentials, generate tokens, and each one of these sites only has to do one thing, which has the ability to validate a token. If a token comes in, be able to crack it open, look at it, validate it, make sure everything's cool without talking to anybody else. It's all self-contained, right? And then if everything's cool, then I know who you are, I know what permissions you have, and then I can let you do things in the application, right? And so we can centralize things, and then each site's job becomes very simple. which is I am able to accept tokens. And the auth server's job is very simple. I am able to generate tokens. You give me a username and password, I can generate a token. And all my other applications just know how to accept tokens. That's it, right? And it also improves performance and scalability because each one of these individual applications, it all happens in memory. I don't have to go consult anything else to figure out if you're an admin or not because that information is contained inside of the token, just like my passport that I carry with me to the airport, right? It's work to generate this thing, but then once it's generated, I can use it everywhere and it's very high performance, right? For me to be able to get in to the airport. Okay. We have a section here on OAuth because I'm not going to talk about how to like fully implement an OAuth-based system, but I do want to talk about sort of what OAuth is all about and how it works, because OAuth is really taking this concept of a token-based system and kind of bringing it across the finish line to give us a system that can really give us some new cool capability that's hard to achieve any other way, right? Having said that, should you use OAuth as the way that you do authentication in your systems? It depends. It's overkill in a lot of cases. It's going to complicate your life in a lot of cases, but it can also give you some features that no other authentication scheme can provide. And after the break, we'll talk about what those features are and when you may want to consider moving to an OAuth type based system. A token-based system though, when would you move to a token-based system? No OAuth, but just a simple token-based system. Usually it's when you want that single sign-on type capability, when you want to centralize your authentication logic in one place and sort of make things more flexible so that, you know, the token can kind of carry claims with it and sort of those kinds of advantages, right? Instead of something like HTTP Basic, where we're just sending the username and password with every single request, which means every single one of these independent systems is going to have to do this whole authentication process on every single request and then map that stuff into some sort of user object with permissions, where the token can contain all that stuff self-contained. We left off talking about sort of token-based authentication systems. And really the big takeaway from a token-based system, so why we would look to move to a token-based system, is usually because we either want to just centralize how we're handling our authentication, or we want to move towards something where we can perform the single sign-on type capabilities. But now what we're going to do is we're going to take this idea of a token-based system and extend it to create something new, which is going to be OAuth. Now, some people have come across OAuth and they tend to get a little bit sort of confused and they don't really understand what OAuth is all about or how it works, because when they go to read about OAuth, it's kind of a little bit overwhelming because there's just lots of terms and all these descriptions about all these different things and how it works, and it's really hard to get a good grasp on sort of the big picture of sort of why OAuth exists and when it can be super useful. And so we include this section as part of the training course here because we think it's valuable for people to kind of have a clearer understanding about what OAuth is kind of about and kind of how it works, and so that you can make the decision of whether or not this is the kind of system that you might want to implement in some of your kind of places in your architecture, okay? And so I want to kind of demystify OAuth a little here because it's not anywhere near as complicated as what some people make it out to be. So what I found is the best way to kind of describe how OAuth works is to use an actual real example from a site that was developed a while back. And so have you guys heard of a site out there called mint.com, M-I-N-T, mint.com, right? Maybe, maybe not. And so mint.com has been around for a while. They were recently bought by Intuit, and so now they're kind of bigger than they were and whatever. But back in the day when mint.com first came out, the idea behind mint.com was that they were going to provide a way so that there was this website you could go to and basically see all of your financial information centralized in one place. So for example, I could log into one application, one site, and I could see all my bank balances, all my, you know, stock investments, my 401k, all of my credit card balances. So I could do like budgeting and all these other things. And I can get a nice picture of my entire financial situation, right? Without having to log into all these different websites and things. And so it sounds very useful. So the investors in mint.com thought this would be a really, really attractive thing to customers if they could pull it off. Well, how are they going to pull it off? Because, you know, they have to get at all this information so they can present it to their users, their customers. So what mint.com did at the beginning was they said, okay, well, let's do this. Let's contact some of these financial institutions whose information we want to be able to get at. So They contacted, and I'm using Bank of America here as sort of my example. But I'm just picking one, right? But this is how it basically went down. So they contacted, say, Bank of America. I don't know who they contacted first, whatever, but they picked one. I'm going to use Bank of America. So they contact Bank of America and they say, hey, we're a startup. We're developing this new thing. It's called Mint.com. We want to help people centralize all their financial information. So can you give us some sort of API or some sort of service that we can call so that we can get at, account balances and things like that for our customers? Now, what do you think Bank of America's response was to Mint.com? They're like, yeah, you guys are on something. There's no way we're going to give you access to our customers' data. We don't know who you are. We don't trust you. We don't, there's nothing in it for us here. So go away. So then Mint.com went to somebody else like Fidelity or KeyBank or whatever, and they gave the same pitch, and everybody gave the same answer, which is like, no. All right. So the investors of Mint.com decided, well, okay, we don't really have much other choice. So here's what we're going to do. We're going to go ahead and still build the application. And when a new user comes and signs up for their account on Mint.com, they're going to get a little wizard that says, hey, add all of your financial institutions. Cool. So then you pick one from like a drop-down or something like Bank of America, and you click the next button. Boop. And then the next window that comes up says, okay, we would be happy to add your Bank of America checking account to your Mint.com account. Please type in your Bank of America username and password. Okay, and so the user would type in their Bank of America username and password, and they click next, and then boop, no problem. Now Mint.com has access to all your information. They can display it right there. It's great. And then you add all your other stuff, right? KeyBank and Chase and Capital One and all the other ones, right? And for each one, you just type in the username and password for your account at that particular place. Now, your action might be, oh my gosh, well, who would do that? Well, millions of users did that because it's a convenience thing. Because they said, well, you know what, this is valuable enough for me. I want to see all my stuff in one place. And so maybe not the smartest idea, but a lot of users did it, okay? And it worked really well. Customers were really happy. Everything was going great. Now, what happens, what do you think happened when like Bank of America and Fidelity and stuff found out about this? They weren't happy. So they contacted Mint.com and was like, you are asking our users for their username and password that gives full access to their account, and then you're using that to pretend to be them. You're basically acting as them to get at their data. You need to stop doing that. And Mint.com's response was, this is none of your business. This is an agreement between us and your customer. We asked your customer to give us the information. They agreed to give us the information, and we're using the information. You have no say here. And of course, like the banks and things were not happy because they were like, So then Mint.com said, oh, but if you'd like us to stop doing this, we would be happy to stop doing this if you give us an alternative way to access the data that we need. Because all we really need is just read-only access to their balances. That's all we really need. But you wouldn't give that to us, so we just asked for their full access with their username and password, and they gave it to us, and that's what we're using. So if you'd like to give us a better way to do it, we'd be happy to use that instead. But when they told these banks, well, give us another way to give us a better way to do it, and we'd be happy to use that, they kind of sort of strong-armed the banks into doing it. And so then they were like, all right, fine, we'll give you an alternative way to obtain the data you need, because that's going to be better for our customers and everything else. And so they kind of worked their way in. And once they were able to get a few, like Bank of America and Fidelity and whatever else, then they can go to these other banks and be like, well, they're giving it to us and they're giving it to us, so you should give it to us. And then they just sort of worked off that, and eventually they were able to get access. Now, what is this alternative way to be able to get at this data? That's where OAuth comes into play. Okay. And so the situation that we have here is a partial trust scenario, because what we've got is I want Mint.com to be able to have some permissions to get at my data, but not full permissions, because I don't fully trust them. I only partially trust them. I trust them to be able to see what my balances are so they can present it to me. I don't trust them enough to give them everything. Okay. But again, at the beginning, Mint.com didn't have any other choice. So they went with sort of just, asking their usernames for their credentials. So here it says OAuth. So this is how we're going to pull this kind of system off, right? OAuth specifies how a client application can request access from an authorization server and present the token to a resource server, solves the problem of a web application trying to access another web application on behalf of the user without having to share the credentials. That's what we want to avoid, okay? So allows for limited valet key type scenarios. We call this a valet key type scenario because you want to give the valet the key that can be used to move the car, but you don't want to give him access to the glove box and the trunk and all that kind of stuff, right? Partial trust. Okay, so OAuth can be used and work very well for this partial trust kind of situation. And what I found is that most people have encountered this at one time or another, because they're on Facebook or something and they come across some little app on Facebook that says, hey, if you fill out this questionnaire, we'll tell you what kind of tree you are. Oh, okay. And you click it, and then it redirects you off to some other little page on Facebook that says, hey, this app is asking for permission to access your friends list and your blah, 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 blah. Are you okay with that? Yes or no, right? And you say yes, then that app is able to access whatever data you said was okay, and then you can answer the questions. It'll tell you, what kind of tree you are or whatever. And that's an actual implementation of OAuth as well. So let's go to this mint.com example here for a second. So what does this actually look like to make this work? So the first obstacle that people typically run into when they're learning OAuth is some of this terminology. So these are the 4 basic roles when we think about the OAuth picture, okay? So the first one is the resource owner, okay? The end user who grants access to the protected resource. So the first thing is, what is the resource? The resource is the thing of interest, right? And in our mint.com example, the resource is the checking account balance, okay? That's the interesting piece of information. The resource owner is the owner of that protected resource. So in this case, it's you, because it's your checking account, right? So you are the resource owner. The resource server is the server that hosts the protected resource and is capable of accepting access tokens. So the resource server is the bank, okay? Because the bank is the thing that hosts the information that holds my checking account balance, right? The client is the application that wants access to the protected resource. So in our example, the client is mint.com. Because mint.com is who wants access to that protected resource, okay? The authorization server, the server that issues access tokens to the client application. Many times the authorization server and the resource server are the same thing, but they could actually be separated from each other, okay? Okay, so in our scenario here, we've got the resource owner, who is you, the resource server, that is the bank, and the client, that is mint.com. Now, I want to have some sort of system here to be able to pull off this kind of partial trust kind of scenario. Now, if I'm going to put something together that's going to allow for partial trust, I have to make sure I don't sort of make a mistake here and violate the rules here about who trusts who and who doesn't trust who, right? So I have to make sure that things happen in a specific way. So we'll see how that happens, okay? All right, so one thing I want to throw out here, because this is going to be relevant in a minute, is when we talk about OAuth, there are 2 different types of clients. Now remember, who's the client? Well, that's mint.com. Okay, so there are confidential clients, clients that are capable of maintaining the confidentiality of their credentials. So server-side code, things that are running on a server somewhere. And then if it's like something like JavaScript or something that's running in the context of a browser, we consider that to be a public client, okay? So for example, in the case of mint.com, when Mint goes to access my data, if it's server-side code on Mint's server that's accessing my data, that's one thing. If I'm on the mint.com website and I end up downloading some JavaScript, and now that JavaScript tries to call to get my bank balance from the bank, so it's Mint's code that's calling my bank, this is considered a public client, okay? Now, in the case of OAuth, there are certain things that confidential clients are allowed to do, but public clients are not allowed to do, okay? So we'll come back to that in a second, okay? There's 2 different client types. Okay, so authorization grant, authorization code grant, okay? Authorization code is the credential representing the resource owner's consent to allow or grant access to the protected resource. There are different grant types, blah, 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 blah. This is not important because we're gonna walk through it here. So this is the slide that sort of walks through in words how this works. But the best thing to do is just kind of talk through it a little bit. Now, sometimes I do this by like drawing on the whiteboard or whatever, but because we have people remote, whatever, I'll do it slightly differently here, and we'll kind of go through how this works. So how is the flow going to work here? All right, So the first thing that has to happen is that Mint.com and the bank have to talk to each other, right? So they establish some sort of agreement that, the bank says, okay, Mint.com, we will allow for limited access to some of our customers' data. So the two of us need to kind of coordinate here a little bit. And so like, for example, Mint.com will sign up for an account with the bank, some sort of like API account or something. And so they'll exchange a secret key so that both Mint.com and the bank have some sort of secret key. And then the bank also has some sort of identifier, some access key, okay? Cool, so they have an arrangement, right? Now, I sign up for my account on Mint.com. I'm a new customer. I click on the button, Mint.com, that says add my bank account. The little wizard comes up, says which bank do you want to add? Here are the ones that we currently support. If you pick one that's supported, then this whole OAuth thing is going to happen. If you pick one that's not supported, then they'll probably just ask you for your username and password because that's the only way they can do it, right? Okay, by the way, this whole Mint.com thing, right? You may think to yourself, wow, it sounds like they were kind of playing with fire here because they were asking for people's usernames and passwords and keeping them and using them like this. If something bad would have happened and this stuff would have got like compromised and, yeah, it would have been game over, right? Investors would have lost all their money. Some people may have gone to jail, who knows what, but that didn't happen. And so luckily they pulled it off and they ended up selling their company to Intuit and they all made, tens of millions of dollars. So anyway, it's, you play the game, you take the risk. Okay, so here though, how's this gonna happen if it's one of the supported banks? So we pick Bank of America and we click next. Okay, then what happens? Well then, when you click the button that says next, you're on Mint.com, right? Mint.com is gonna redirect you over to Bank of America's website. So it's gonna redirect you to like bankofamerica.com/mint/something, whatever, question mark, callback equals some URL, right? Foo, okay? Let's just do that, okay? So you click the button, it sends you off to Bank of America's website, and you get presented with some sort of little form, okay? Now, because you're going to this Mint page over here on Bank of America, let's call back. So Bank of America knows that when you go here that, oh, this is somebody from Mint.com that's, trying to, establish an account or whatever. So Bank of America knows what permissions they're going to allow in this situation. So Bank of America pops up a little box that says, hey, Mint.com is asking to get access to your bank account balances and, your account numbers and blah, 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 blah. Are you okay with that? You say yes or no, right? This is important though, right? Because it's not Mint that's asking here. This is the bank that's asking. I'm talking to my bank's website. I trust my bank. So they're the one that's asking me what permissions I would like to give to Mint. So I say, yes, that's okay, that's okay, that's not okay, that's not okay, that is okay. Click, yes. Bank of America records my consent and what things I've decided to allow Mint to do, and then redirects me back to the callback URL, which is this one here. So this is probably like, actually, mint.com/something, something, 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 right? And when so now it redirects me back over to mint.com, and it includes a authorization code, all right? So like 652 or whatever, okay? So it redirects me back to mint.com. So when it sends the redirect back to my browser then makes a request to mint.com and sends this auth code. The mint.com server then receives this auth code, and now mint.com takes this auth code and uses it to make a call to Bank of America's web API. Now, when it makes the call to Bank of America's web API, it includes its access key ID and uses its secret key and includes this auth code. And then what Bank of America does is basically receives the auth code and says, okay, is this auth code valid? Yes, yes, we just issued it 3 minutes ago to this request. It goes with this user, with these permissions, da 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 da. So then Bank of America generates a access token. So it creates a token that contains claims and permissions and anything else we want to stuff in there and a signature, and returns that token to Mint. So Mint basically exchanges this auth code for an access token. Now Mint has an access token. So now once it has that token, now Mint uses that token to call the Bank of America API to get my account balance, and to get anything that it has permissions for, right? Because it's basically just using that access token as its way to access my stuff, okay? But again, that access token only contains the claims which I authorized Bank of America to give to Mint, which is read-only access to my account balance, et cetera, et cetera, et cetera, et cetera, right? So now Mint is just talking to Bank of America, you know, every 10 minutes, whatever, so it can give me up-to-date information about what my account balances are. It can call it as much as it wants in the background, you know, server to server. And every day when I log into Mint, I can see what my balances are because Mint in the background is talking to my, you know, bank, getting this information. Okay, now, what happens when, like 2 weeks later, I decide that I don't want Mint talking to my bank anymore because I've canceled my account and I don't want them to do that. And I've decided to go with somebody else. Well, what I don't do is I don't log into mint.com and say, hey, Mint, please stop accessing my data, because I don't really trust them in that way, right? Instead, I log into my Bank of America account, go to my little, you know, user profile or something, and there's going to be a list there of all the people I've granted access to my data. I see Mint listed there, and I click the revoke button, and basically tell Bank of America, stop giving access to Mint, okay? Because I trust my bank to do that, to shut them off, right? In the other case, where I just gave Mint my username and password, if I want to stop Mint accessing my stuff, I really have no choice other than to like change my password, which is going to be really inconvenient. Also, if I change my password for other reasons, I just broke Mint's ability to get to my data. So in both regards, it's wonky, right? Doesn't work well. In this case, it's much better. It's much cleaner because now, notice something about this little situation here is the access token, the thing that Mint uses to get at my data, never goes through the client. It doesn't pass through the browser, right? I'm on mint.com, sends me over Bank of America. I tell Bank of America what's okay. I get that little auth code, which I send over to Mint, and then Mint exchanges that auth code for a token. The token itself, though, never goes through me, okay? And that's good because that's like a secure thing, right? And now Mint has the way to access my data. Now, yeah, pretty much. Well, I mean, so it's both, right? Because when I walked through this kind of example here, I make the request to Mint. Mint redirects me to Bank of America, so I'm looking at the Bank of America page. I say what permissions I want. That posts back to Bank of America. Bank of America then sends a redirect to me to go back to Mint, but that redirect includes that authorization code. So then Mint receives the authorization code, and then yes, server to server, Mint exchanges the auth code for a token. But we bring that authorization code into the picture because we don't want the auth token to travel, you know, over the internet through the client, okay? Because that's just between these two parties. Okay, so the token, the access token that's issued by the authorization server is based on the authorization granted by the resource owner. So, but remember, in this little scenario here, I'm telling Bank of America what's okay. I'm not telling Mint what's okay because I don't trust them to respect my wishes, right? I'm telling the bank that's what's okay so the bank can control access of what Mint's allowed to do, right? The client accesses the protected resource by presenting the access token to the resource server. The resource server validates the token for freshness and scope. So in other words, Bank of America, when Mint makes the call to get the balance and it submits that access token that it obtained, Bank of America just checks to make sure, is this a valid token that we issued? Yes. What claims are contained within it? And then it uses that to provide access to the resource. But again, for performance reasons, Bank of America does not have to go back and check a bunch of other stuff to make sure that this is okay, because the token itself contains all the permissions, all the claims, right? And Mint can't mess with that because, like we talked about before the break, this is a token-based system. So Mint can't mess with the token because if they mess with the token, they're going to screw up the signature that's in there when Bank of America sort of minted the token, right? Now, and a lot of times, actually, the token is opaque to the client. So in other words, Mint.com has no idea what that token contains. It can't read it. It can't do anything with it. All it does is it just knows that when it got this token from Bank of America, it's stored it in the database associated with my user account. So whenever it needs to get my information from the bank, it just knows to send that token to Bank of America, and that'll allow it to get the access. Okay, but the typically the client, Mint, doesn't know when the token expires. It doesn't know what claims are contained in there. It doesn't know anything. It just knows that, hey, when I want to get Joe Smith's balance, this is the chunk of stuff I have to send to Bank of America, right? Totally opaque and not modifiable, because if it, again, there's a signature in there, so if they modify it in any way, the signature, it won't be valid anymore, okay? Now, what happens when the token expires? So, Bank of America issues this token, and the token has baked into it an expiration date. So every time Mint calls the bank checks to see if the token has expired, right? Because it's able to decrypt the token and, you know, whatever. What if the token is expired? Well, then Bank of America doesn't allow access. Basically tells Mint.com, sorry, this token's expired. You need to get a new one. So then Mint is like, well, shoot, how do I get a new token? Well, I'm gonna have to do this whole process again. So that means the next time the user logs into Mint.com, you're gonna have to give a message to the user that says, your access, the ability for us to get to Bank of America has expired. So you need to reauthorize us to talk to Bank of America. So then this whole little process we just walked through has to happen again. So Mint.com redirects you to the bank, you tell the bank it's okay, the auth code comes back from the bank, you send the auth code to Mint, Mint exchanges the auth code for an access token. That's painful. We don't want to have the users doing that every single time. So OAuth introduces the idea of a refresh token. This is actually, I think this is kind of the coolest part about OAuth that somebody was thinking here. So a refresh token is a token that can be used for one thing, which is to obtain a new access token. So I go to Mint, I go to add the bank, sends me to the bank. I say, yep, that's okay. Bank sends an authorization code. I send that to Mint. Mint exchanges the authorization code for an access token and a refresh token. Mint stores these two things in their system associated with my account. So then a couple of days later, Mint is like, hey, I need to get the balance for Joe Smith here. So I'm gonna call Bank of America, I'm gonna use this access token. Got the balance, great. A couple of days later, I'm gonna use this access token to get the balance. Bank of America returns an error, says that token has expired. Oh, okay, throw that away. Use the refresh token to call a different API method over there, which basically says, please give me a new access token. Here's the refresh token. It validates the refresh token, says, yep, that's cool, and then issues a new access token. Now, Mint uses that access token to gain access until it expires, and then it uses its refresh token to obtain a new access token. What's the point of doing this? Why are we adding this additional complexity? It's a performance thing, because you got to think about this for a second, right? If you're Bank of America and you're putting out an API like this API has probably got some pretty heavy load on it, right? Thousands, tens of thousands, millions of requests per second, whatever it happens to be. And so I want the process of validating an access token to be very, very, very cheap and very fast. So Bank of America, when it goes to validate an access token, all it checks for is this a valid token? Meaning, does the signature match up and everything? And has it not expired? If those two things check out, it allows access. Without talking to any back-end things or looking at anything else, it's all just all self-contained within the token, right? But here's the problem. What happens when the user wants to revoke access? So the user logs into their account and they bring up the list of things and they say, no, revoke access to Mint. Boop. So that sends that request to Bank of America. Bank of America then records that information that Joe Smith has requested that access to Mint.com be revoked. That's stored in a database someplace, right? But that revocation is not checked when Mint makes a call using an access token, because making that check could be kind of expensive. So we don't make that check, okay? Instead, we just allow, if it's a valid token, we just allow access. But now when that thing expires and then Mint says, please give me a new access token, here's my refresh token. When that operation occurs, then the bank says, well, hold on here. Before I issue a new access token, there's a bunch of stuff I need to check. Has it been revoked? Have other things happened? You know, what's going on? Blah, 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 blah. Can do a whole bunch of extra more additional work before it actually gives out a new access token, okay? And so that way, Mint.com can be making, thousands of requests per second using access tokens, and it's all very, very fast. And then when those things, as they expire, then that other operation, that refresh token operation happens, which is much slower, but doesn't happen anywhere near as often. Now, the key here is it's up to the bank to decide how long an access token lives for. So the bank could decide that an access token only lives for 5 minutes, 20 minutes, whatever, or an access token could live for days or weeks, okay? But that's where the bank gets to have this balance between performance and security. So if we say an access token can last for 2 days, the problem there is the bank issues a new access token. The user immediately logs in and says revoke access. Well, Mint's going to continue to get access for 2 more days, okay, until the next refresh comes along. On the other hand, if the bank says no, access tokens only live for 20 minutes, well, then when the user clicks revoke, it's going to take effect pretty quickly, no more than 20 minutes. But now you're trading off performance a little bit because now these refresh operations are going to happen more frequently, okay? But it's cool because it gives the bank that option, that freedom, right, to choose how long access tokens live and kind of make that balance between performance and security. Or the bank may decide not to use refresh tokens at all, or could have very, very short-lived, or it's nice to have choice, right? Not really. It really comes down to sort of, what the bank feels is appropriate for their customers. Or the bank could potentially even let the customer choose. And so they can pick, I haven't seen an example of that, but usually it depends on the kind of data they're allowing access to and what the permissions are like and things like that. But yeah, there's no sort of, it's so highly variable depending on the application. Now, one thing though that is important is this whole refresh token idea. Remember when we talked about the 2 different kinds of clients? So the confidential clients and the public clients? Only confidential clients are permitted to receive refresh tokens. Okay, because a refresh token is sort of a valuable thing, right? It has the ability to get new access tokens. So in the case of where Mint.com, everything is server to server, the Mint.com server can receive a refresh token to be used to get future access tokens. On the other hand, if it's a public client, so this is like a, Mint.com's Angular app or something, and in JavaScript, it's calling directly from JavaScript to the Bank of America API, it can receive an access token, but is not allowed to receive a refresh token because that JavaScript that's executing in the context of the browser, we don't trust that client enough to maintain the confidentiality of that refresh token. And so it's not supposed to get one, okay? So it kind of depends a little bit on that, but yeah, so now the question that immediately comes up then is, okay, so this OAuth thing sounds really interesting. It allows us to provide a way, a standardized, well-defined way to do this kind of partial trust scenario, right? Okay, so what's involved if I do want to implement this kind of thing in my own applications? Well, it kind of depends on who you are in that picture, okay? There's 3 different places where you could be in that picture, okay? One, you might be Mint in that scenario. If you're Mint in that scenario, your job's probably really easy because if you're Mint in that scenario, all you have to know is, okay, what URL do I send them to at Bank of America to get the access code? And then once I get the access code, what API do I call with that access code to get the token? And then how do I send that token when I call the API? And that's all stuff that's probably in the Bank of America documentation or whatever, and it's probably really straightforward. We're talking a couple dozen lines of code. It's probably very simple if you're Mint in that picture. On the other hand, if your role is the bank in that picture, so you're the one that has the protected resource and you want to have a way to allow other parties like Mint to get access to that resource, now your job is much more difficult because now you have to write the code to generate these access tokens, to generate these refresh tokens, to generate these access codes, to provide some sort of UI where users can revoke access to different parties, there's all sorts of bits and pieces involved, right? So when you're the bank in that picture, it gets much more complex. Another way in which OAuth can be used is, let's say you have an application where you would like people to be able to log into your application using their Facebook account or their Google account or something. A lot of frameworks now like ASP.NET Identity have stuff built in that makes that process actually very, very easy to allow people to log into your app using their, Facebook, Google, whatever. Yeah, that's easy, and that's kind of OAuth behind the scenes. If you're Mint, then that's, again, pretty easy. If you're the bank, what Microsoft actually recommends, and most other sort of web framework vendors recommend, is that you don't try to code all that yourself. Instead, you look to some other third-party framework or toolkit to build that. And the one that's sort of most popular now in the Microsoft space, and the one that Microsoft actually recommends, is Identity Server. So Identity Server, if I was to go over here and let's go to github.com/identity server. And so we can see it says, Identity Server is a free open source OpenID Connect and OAuth 2 framework for ASP.NET, founded and maintained by blah, 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 blah. Incorporates all of the protocol implementations and extensibility points needed to integrate token-based authentication, single sign-on, and API access control in your application. Is officially certified by the OpenID Foundation and is spec compliant, blah, 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 blah. So, again, if you're the bank in that picture, you're the owner of the resource, using something like this is probably going to be the best way to go. Having said that, if you go back to that book that I mentioned earlier, that Pro Web API Security, there is actually a couple of chapters in that book that actually will walk you through building an entire OAuth implementation totally from scratch. Very ugly. I worked through it once and I was just like, I never want to do that again, because there's just so many bits and pieces involved and everything else, and making sure you get it all right. We use something else. And even Microsoft didn't bother building this because they were like, this is security related stuff. You know, there's a lot involved making sure everything's done correctly. So you know what? These guys have done a really good job. Just use their stuff. And that's what they officially recommend. So sweet, okay. And there's other ones that are out there. This is just the one, like I said, in the Microsoft space that's kind of the most frequently used, and it's mature. It's been around a while. It's well supported. There's lots of documentation out there. It's really, really, really good stuff, okay. And so if you're going to go down that road, that's probably sort of what I would look at there for that, okay. But again, don't just use OAuth because you think, oh, it's cool, it's new, because, you know, we're obviously adding quite a bit of complexity here versus like the PSK system that we looked at earlier, okay? However, if we've got this kind of partial trust sort of scenario, this is the way to do it, okay? Because otherwise, pulling off that kind of partial trust kind of thing is really, really tricky to figure out an effective way to do that. And so that's why OAuth is there, right? Partial trust, okay? And in the web, that comes up quite often, right? I don't want to give the what tree of my app full access to my entire Facebook account. It'd be ridiculous, right? I just want to give it certain things. And sometimes, you know, when that little dialogue comes up that says, hey, the what tree are you app wants access to, and it lists all this crazy stuff, and then you're like, oh no. So you cancel that and move on, right? And that's good. That's want to make sure that the users have visibility into exactly what's going on here, and we don't have to put trust into that app, because, you know, we're not telling the app what it can do. We're telling Facebook what the app is allowed to do. And that's the key bit, right?